Hello YouTube and welcome. This video is a response to a video from Anthony Riley in which he shows a video from someone called, I think, Taboo Conspiracy. I'm going to play a part of Anthony's video just at the beginning so that you can see what Anthony is claiming, and then I will address those claims.
Okay, this clip has been allowed to be recreated courtesy from the copyright holder, Taboo Conspiracy. For the purposes of this video, I'm not that interested in exactly where it is or its coordinates or its GPS or any of the meta bumps that everybody requests. All I'm interested in is what does Google show compared to what does it show in real life. Now, Taboo Conspiracy has done this video in some mountains. You can look them up if you wish. It's not important. But what he's showing, conveniently, is that the curvature shown by Google Earth does not match that which we see in the real world. Now, my question to you, if you're watching this, is what is the curvature that we are seeing on Google Earth? Why are we not seeing it in real life?
So Anthony's claim is that what is seen on Google Earth in this video is not what is seen in real life. So let's have a look at that claim. So these are two stills taken from the video in question by Taboo Conspiracy that Anthony is referring to. And the claim is that the view from the camera here does not match what is seen in the same view taken from Google Earth. Now, obviously, it's slightly difficult to get an absolutely perfect match between the view from the camera and the view from Google Earth. First thing to point out is the width of the field of view. This is a minor point in what I'm going to say, but it's worth noting. So this peak just here is actually the very far left of the camera view. So all of this is, on the right hand side here is absent in the camera view, but is present in the Google Earth view. And on the left hand side here, this slightly curved piece here, this corresponds to this section, and then there's a short flatter area here, and we're probably missing from about where there seems to be a tree line or a change of color here on the Google Earth image. This is absent. This may in fact be hills in the background or something. This seems to be largely absent from the camera picture. The camera picture is a far narrower angle, a narrower view than the Google Earth picture. But this isn't a crucial point in the analysis that we're going to see, but it's important just to bear it in mind. We're not comparing exactly like with like. So here we are on Google Earth, looking at the same view as is shown in the video that Taboo Conspiracy and Anthony Riley have shown. The point being made, certainly by Anthony, is that what we see in this Google Earth image and another one I'll show you in a moment is different to what the camera actually shows. The claim is that all we see here are the Traverse Mountains and these mountains going along the side here, and that we are not seeing mountains beyond the Traverse Mountains in the distance here. This is because Google Earth hides those mountains because the Earth is curved. And so as the land falls away in front of us as we look at it here, the claim is that the mountains are in fact hidden behind the curve, and we can only see the near mountains, the ones that are 25 miles away. Now, vantage point here is over 6,000 feet above sea level, so we're not looking from ground level or sea level. We are looking in elevated position, but even so, the claim is that the mountains are hidden beyond the curve. Now, the question is that really the case or not? And there are two reasons for thinking that it is not. The first reason is one of resolution. Now, Anthony says it's nothing to do with resolution. The mountains are hidden beyond the curve, and that us globe Earth people just have to accept that. Well, Anthony, I'm afraid I don't accept that for reasons that I'll go into in a minute. But this isn't the main thrust of my argument. It's an important but additional point to my main argument that I'm about to get to. The resolution is actually important. Even in this view that we're looking at here, a single pixel is quite a considerable height of land or mountain or hillside. You can see that because the mountains here are not a smooth shape, but they are stepped. There is a stepping effect because there are not enough pixels to actually smooth out this this height. And we're talking about fairly high mountains and hills here. So the difference between the shoreline here and the top of the Travers Mountain highest peak is something of the order of 1,800 feet. So each pixel, if there are 18 pixels there, each pixel at that distance is 100 feet. And on a later view, we'll see even fewer pixels involved. However, let's get to the main point. And the main point is that Google Earth has various tools and things, and it has something called borders and labels. And if we click on borders and labels, it highlights in this turquoisey blue color the borders that exist in the view that we're looking at. And what we see by doing this is that there is a border that runs along here, and it actually runs along the top of the Travers Mountains, and it runs along these mountain ridge here and up to the top and over that way. To the right, we can see also that there are other border lines that are beyond this Travers border line. There are at least two clearly visible lines, and it also highlights the stepping effect of the pixels because the resolution here, we are condensing many miles of distance, many feet of height into very few pixels, and so to represent that is very difficult. We can also see that above the Travers border, and we can see this Travers border here, we can see things appearing above that border. And actually it appears that there might even be another piece of border. If we change the view to a no atmosphere view, you can see a little bit more clearly where the border markings are. And I'll put the sidebar back on and we'll click this off. Okay, and then click it back on and click it off. Whoops, click it off and click it back on again. And you can see that the border lines appear and are well beyond the, or above at least in this view, the Travers border, and even on the horizon here there is another border. Now I'm going to go down to Street View because I don't want anybody to accuse me of being a little bit fast and loose with Google Earth here. I'll just put on a line which runs from our camera viewpoint to Willard Peak, just to help to guide this. Okay, if we go down to Street View, what we see with the borders does change a little bit, and I'm perfectly happy to concede that. So here we are at Street View, and what has happened is the whole image has become more compressed. It's widened And so what things that were quite high are now even lower, even narrower amount of space, even fewer pixels dedicated to those things. But if we look at the borders, we can still see that these border lines that we were looking at before have uh, are still present, are still clearly visible. Now, this is not the transverse borderline, and in any event, there's still at least two of them. The transverse borderline is actually almost invisible from our view. We can just make it out here and going up, and that's partly because it doesn't run along the highest point of that peak. So when we were looking from a slightly more elevated position, we could see it, and when we're looking from a lower position, we can't see it so clearly. But in any event, there are borderlines beyond the transverse border, and here the transverse border is coming down, and on the horizon again we see another border line. So exiting ground view to see what these borders actually look like. And if we go up a bit in the air, we can see the borderline that goes along the transverse mountain ridge and goes up, and we saw it going up to this peak quite far on the right hand side, and our field of view is through here. Just to highlight the point that the transverse border is not necessarily at the highest point and is not always visible along here. It is in places, but it's not always. For example, this peak here is actually up at 2000. It's about 2040 meters if you get the cursor on exactly the right spot. And the bit of border behind it is a sort of 80 meters lower down. So on Google Earth, we wouldn't expect to see this border in its entirety, especially when we're down at street view and we're looking up over peaks here towards the border here. In any event, we could see other border lines beyond these or above this one. So where are they? Well, here's one which runs up to the top of the ridge here, and there is another one beyond, and I thought we distinctly saw two borderlines. There are borderlines running along the ridge as well, and in the background we have Willard Peak here. So the contention that we cannot see these mountains from our viewpoint across the transverse mountain range, little hill range here, is, I think, completely bogus, because we see this borderline, and I think we see this borderline here as well. Maybe we see part of this one, but we certainly see some of these mountains, in spite of the fact that we are in a highly compressed situation with very poor resolution, with 1 pixel corresponding to several hundred feet of height. So the question now is, well, what should we see on a flat Earth? What should we see on a globe Earth when looking at this particular view? And I've tried to make some diagrams to look at that. So let's have a look at those diagrams and see what we should see. So I decided to draw some diagrams, and this was quite challenging. I just got AutoCAD, and it's quite a complicated program, and I'm really not familiar with it at all. And I toyed with the idea of using a scale which was different on the horizontal to the vertical, and then opted to just keep everything scaled the same. And I'll zoom in after we look at the first view so that you can see in a little bit more detail exactly what the effects are and what we ought to be able to see. So bear with me if this looks small on screen, it'll get bigger later on. So on a globe Earth, we have a curve. And if you draw a straight line across this curve that I've done, I've made the curve to scale exactly 90 miles long. Well, it's scaled to represent 90 miles, and the gap at the end between the straight and the curve, if you add those two bits together, you get to just about exactly a mile, and that is exactly the drop that you would expect on a globe the size of the Earth. We'll check that on the curve calculator later so that you can verify it, but this space here plus this space here is 1 mile. So at 0 miles, we have West Mountain, which is where the camera is, and the camera was located at 6,820 feet above sea level, according to the video. And Traverse Mountain is very similar height, a little bit lower, but not very much, and is at 25 miles. Again, this is to scale, so this is 0 to 25 and 90 at the end, and Willard Mountain, a taller mountain, at 9,760 feet above sea level. So I've drawn little triangles to represent the mountains, again to scale. So we have West, Traverse, and Willard. And if we draw a line of sight from the very top of West to the top of Traverse and continue it on to Willard, this is what we get. Okay, and I'll zoom in later so you can see exactly what is being seen here, because again the resolution on the screen is not sufficient to really reveal what is going on. Now on a flat Earth, using the same distance, just drawn a narrow rectangle here, and we have exact copies of the triangles placed on the surface and a line of sight drawn from West to Traverse and on to Willard, and we get this. So is this what we actually see in the camera image in the video? Well, I'm going to go to a non-full screen version of this diagram so that you can see exactly what is going on here, and then we can compare it to the camera. So here we're on the non-full screen version, and this allows me to zoom in to the diagram, and if you look here, we can see the West Mountain and the line sitting right at the top of West Mountain, line of sight. It goes right across the top of the Traverse Mountain peak here and on to Willard Mountain peak, and doesn't hit the top of Willard Mountain peak. It is going just slightly below Willard Mountain, very top. So we would expect on a globe to be able to see the very, very top of Willard Mountain protruding above the height of Traverse Mountain. Now, on the flat Earth, and the same thing is drawn here, you can just check going from the very top of West, or the point at which the height at which it was stated the camera was at on West Mountain, across directly the top of Traverse Mountain to Willard Mountain here. We'd expect to be able to see almost a half of the height, somewhere between a third and a half of the height of Willard Mountain, Willard Mountain being 9,760 feet above sea level, and you would expect to be able to see on a flat Earth some 4,000 feet or more of Willard Mountain above the height of Traverse Mountain. So is that what we actually see or not? So before we look at the camera views again, let's have a look at Metabunk curve calculator very quickly. I know it's Anthony's favorite calculator. And I've put in a distance of 90 miles. I've put in a viewer height of 0 feet to get the maximum drop and other values that you would get on a globe. And as I said, the drop at this distance of 90 miles is almost exactly 1 mile, just very, very slightly more than 1 mile. And this was the amount that we had on the diagram. So the diagram corresponds to what the curve of the Earth should actually be. So returning to Anthony's video for one last time, let's have a look. The image, the Google Earth image, the claim is that this doesn't represent what we see in reality. Well, let's play the video. What did it look like in reality? Here we are with the image of the Traverse Mountains, and here is the Google Earth image. I'll pause it here. We've already seen that there is land which is mountainous, we know, beyond this point here, which is clearly visible on the Google Earth image when you highlight the borders. And as we zoom in, these mountains, this area here comes into view. And it is in view in the camera, and it's in view on Google Earth. So the borders that are running up and along these mountains highlight on Google Earth, and therefore those borders are visible on Google Earth. It's just the resolution that makes it difficult or impossible to actually make out that there is another range of mountains visible beyond the Traverse peaks here that are 25 miles away. So we've no issue with these mountains being visible at all. We're quite happy with that. This is what we see on Google Earth as well as what we see on the camera. Now the issue of Willard Peak. So the height that we actually took in the diagram was the highest point on the Traverse Mountains, which is here. And the peak that is compared to in the video here where we zoom in is this one, which is actually a little bit below the height of this one. It's probably about 30 meters lower. So what you have to imagine is in our diagram, we were looking over the top of this, and we were seeing just the very tip of Willard Mountain above this. And so as we zoom in, what do we actually see? Well, here's the Willard Mountain peak. It goes up to about this point here, which is clearly above this peak here, and will be maybe just above, possibly even level with the other peak. Certainly pretty close. And so as identified in the video, this is Willard Peak. I'm not making it up, and it's only a tiny bit showing above this peak, and maybe even less, maybe half or less than half of that distance there above the highest point of the Traverse peaks. Now, what did we calculate from our diagram that we should see on a flat Earth? We calculated that we should see 4,000 to 5,000 feet of Willard Peak above the height of the Traverse Mountains. Now, I don't know about you, but I don't think that that distance there is 4,000 or 5,000 feet. If it was, then Willard Mountain, or Willard Peak, would be more than 15 or 20,000 feet high, and that's assuming that the base is here. We know the base is way below there because this mountain's in the way. The flat Earth view, we should see an enormous height of Willard Peak above the height of the Traverse Mountains, and we don't. We just see a tiny little bit of Willard Peak above the height of the Traverse Mountains. And that is exactly what our diagram of a globe Earth showed. So, what can we conclude? Well, we can conclude several things. Okay, so what are the conclusions that we can draw from these images and from our analysis of them on Google Earth and by diagrams and so on? Well, the first conclusion is the resolution on Google Earth makes it difficult to see landscape features in the far distance. This isn't the most important conclusion, but it's certainly a conclusion we can draw. And anybody can check this. If you're looking at things in the far distance on Google Earth, then you are going to be seeing you're only going to have a very, very few pixels available to resolve features, and therefore you're not going to be able to make those features out very clearly. Second, the real view taken with a camera and the view shown on Google Earth Street View are almost identical. We can come to this conclusion because the camera image we have identified is a narrower angle image, and it has the effect of magnifying the area in the center of the Google Earth Street View image. The tools that we have used to highlight features on the Google Earth Street View image show that the things that we can distinguish on the camera image are in fact present on the Google Earth Street View image. And so the images appear certainly very similar, almost identical, maybe a little strong, but certainly very, very similar. The third conclusion is that the real view taken with a camera and the view shown on Google Earth both agree very closely with a scale drawing of the scene, which is based on a spheroid Earth of 3,959 miles radius. That's the radius used in the Metabunk curve calculator. And this is what we used to base the scale diagrams on, and the scale diagrams agree very, very closely with the images shown by the camera and the view shown on Google Earth. 4. The real view taken with a camera does not agree at all with a scale diagram based on a flat Earth. And so our scale diagram based on the Earth being flat showed that we should see the Willard Peak appearing very, very high above the Traverse Mountain Peak, and in point of fact we do not see that at all. We see only a very small amount. So there is no agreement between a flat Earth scale diagram and the image that we actually see. And so we come to our main conclusion that we can draw from this set of data. It's not conclusive, but the main conclusion that we can come to is the Earth is not flat. Thank you, Anthony Riley, for providing such fantastic evidence that the Earth is in fact a spheroid and has a curve that matches exactly what you see in reality.